In the grand pantheon of prehistoric life, one name echoes with the weight of undisputed authority: Argentinosaurus quinquelensis. It is the benchmark for biological scale, a continent-shaking titan whose very existence seems to defy the laws of physics. Pop culture and documentaries have crowned it the heavyweight champion of Earth, a walking mountain of flesh and bone that made even the mighty Tyrannosaurus look like a mid-sized predator. But in the world of paleontology, absolute certainty is a rare fossil, and the bigger the claim, the heavier the burden of proof. The question that has haunted scientists for decades is not if Argentinosaurus was big, but precisely how big. What was its true weight? Was it a 50-ton giant or a colossus pushing the 100-ton barrier, the biological equivalent of a Boeing 757? Answering this is the key to understanding the absolute upper limit of life on land. Now, let us follow the evidence written in the fossil record, decode the science hidden in the bones, and witness the final verdict in a battle millions of years in the making. Our investigation begins not in a pristine lab, but on a remote farm in Patagonia, Argentina, in 1993.
Incredible.
It was there that paleontologists José Bonaparte and Rodolfo Correa unveiled the first, and to this day, the most significant remains of this Cretaceous behemoth. The world expected a near-complete skeleton, a titanic frame to match the legend. The reality was profoundly different. The giant's entire legacy, the foundation for every weight calculation to follow, rests on a handful of colossal yet tantalizingly incomplete clues. The fossil evidence is staggering in its size but shocking in its scarcity. What we have are a series of dorsal vertebrae from the creature's back, each one measuring over 1.5 meters or 5 feet in height. We have fragments of enormous ribs that arched like the internal scaffolding of a cathedral. We have the sacrum, the fused vertebrae that connected the spine to the hips, and a single immense tibia, or shin bone. And that is largely it. No skull, no tail, no neck, no forelimbs. This wasn't a skeleton. It was a paleontological crime scene with most of the evidence missing. The bones were the murder weapon, and the victim rolled into one, clues to a life lived on a scale almost beyond comprehension. This profound lack of data is the heart of the Argentinosaurus problem. Imagine trying to calculate the exact weight and dimensions of a supertanker having found only a few pieces of its hull and a single propeller shaft. Early paleontologists had to engage in a process known as extrapolation, essentially an educated guess on a colossal scale. They looked at more complete skeletons of related but smaller sauropods like Saltosaurus and Rapidosaurus and attempted to scale them up to fit the monumental proportions of the Argentinian fossils. The problem? Titanosaurs, the group to which Argentinosaurus belongs, came in a vast array of body shapes. Some were long and slender, others were stocky and robust. Choosing the wrong anatomical blueprint could lead to an error of dozens of tons. This vast gulf of uncertainty created a scientific battleground. Initial estimates, often cited in popular media, soared towards the 100 metric ton mark. These figures captured the public imagination, cementing the dinosaur's mythical status. Yet other, more conservative analyses, using different sauropod models, produced figures as low as 60 or even 50 metric tons. This isn't a minor discrepancy. The difference between 50 and 100 tons is the difference between a herd of 10 African elephants and a herd of 20. It's the tipping point between a plausible biological marvel and a creature that seems to break the rules of biomechanics. To find the truth, we must move beyond simple comparison and enter the world of cutting-edge analysis, where digital skeletons and virtual physics can reconstruct an animal from the inside out. The fossil fragments are our only direct witnesses, and now we have the technology to make them talk. To move from the realm of speculation to simulation, we must treat the fossils not as relics, but as high-fidelity data points. The first step in this biomechanical deep dive is to bring the colossal bones of Argentinosaurus into the digital world. Using high-resolution laser scanners, we create perfect three-dimensional models of each vertebra, rib, and limb bone. Every crack, every ridge, every foramen, a small opening in the bone, is captured with sub-millimeter accuracy. With these digital fragments as our anchor, the reconstruction begins. This is where the detective work intensifies, leaning on a powerful principle called phylogenetic bracketing. In essence, we look at the immediate family of Argentinosaurus. By analyzing the more complete skeletons of its closest titanosaur relatives, such as Patagotitan and Futalognkosaurus, we can infer the most probable shape and size of the missing pieces. We aren't simply guessing. We are building a chimera not of myth, but of data, filling the gaps in our fossil crime scene with the most statistically likely evidence from its next of kin. With a complete digital skeleton assembled, the next challenge is to put flesh on these virtual bones. This is not the arbitrary work of a movie monster maker. The bones themselves provide a precise blueprint for their own musculature. On the surface of the fossilized tibia and vertebrae, we can identify osteological correlates, the scientific term for muscle scars. These roughened patches, crests, and trochanters are the anchor points where powerful tendons and massive muscle groups once attached. A prominent ridge on the tibia, for example, tells us exactly where a major leg retractor muscle was located, giving us a clear indication of its size and power. By cross-referencing this data with the muscular anatomy of their living relatives, crocodilians and birds, we can digitally reconstruct the major muscle groups layer by layer. This process, known as musculoskeletal modeling, transforms the static frame into a dynamic machine, allowing us to see how the limbs moved and how the animal supported its immense bulk. This meticulous reconstruction reveals one of the sauropod's greatest evolutionary innovations, a key piece of evidence in our weight investigation: pneumaticity. When we CT scan the immense vertebrae of Argentinosaurus, we find that they are not solid bone. Instead, they are a honeycomb of air sacs, an internal lattice of hollow spaces. This was part of a hyper-efficient respiratory system, similar to that of modern birds, where air flowed through the bones themselves. This wasn't just about breathing, it was a masterclass in biological engineering. This pneumatic system drastically reduced the weight of the skeleton, particularly the long neck and massive torso, without compromising its structural integrity. It allowed titanosaurs to achieve sizes that would have been impossible with a dense, heavy skeleton. It was the biological equivalent of using carbon fiber instead of steel, a crucial adaptation for life in the gravitational arena of prehistoric Earth. Now, with a biologically constrained, fully fleshed digital model of Argentinosaurus, we can finally perform the virtual weigh-in. The technique is called volumetric analysis. The software calculates the total volume of our 3D model with incredible precision. But an animal is not a uniform block of material. Different tissues have different densities. So, we segment the model into different components: skeleton, muscle, fat, internal organs, and the extensive pulmonary air sac system. Drawing from extensive studies on modern animals, we assign a specific density value to each tissue type. Bone is dense, about 2.0 grams per cubic centimeter. Muscle and organs are close to the density of water, around 1.05 grams per cubic centimeter. But the air sacs have a density close to zero. When we integrate the extensive pneumatic system into our density calculations, the final mass estimate begins to shift significantly from the old 100-ton behemoth of popular myth. The model, which accounts for the lightweight skeleton and the air-filled torso, becomes substantially less dense than a simple scaled-up reptile. A 2019 study led by Dr. Gregory S. Paul utilized this very method, creating a rigorous digital model that accounted for these complex biological factors. Similarly, research from teams at the University of Manchester has refined these digital techniques, treating the prehistoric giants less like statues and more like functioning, breathing organisms. This biomechanical deep dive transforms the fossil from a static clue into a dynamic, living system. We are no longer just guessing based on a single bone. We are running a physics-based simulation grounded in the totality of the anatomical evidence. The numbers that emerge from these models are not final, but they are the most rigorously tested evidence-based figures in the history of this debate. The stage is set for the final verdict. So after rebuilding this lost titan in the digital realm and subjecting it to the laws of physics, what is the final number on the scales? The verdict from the virtual laboratory is in, and it serves as a powerful piece of paleontological myth-busting. The legendary 100-ton figure, born from simple scaling of incomplete fossils, now appears to be a significant overestimate. Those early calculations, while groundbreaking for their time, could not account for the complex, weight-saving adaptations hidden within the skeleton. The biomechanical models, which integrate the crucial factor of skeletal pneumaticity and use data from a wider range of related titanosaurs, consistently converge on a more constrained and ultimately more plausible figure. The 100-ton titan of legend recedes, replaced by a still staggering but biomechanically sound reality. My final analysis, based on this convergence of evidence from multiple independent studies using volumetric modeling, places Argentinosaurus quinculensis firmly in the 70 to 77 metric ton range. To be clear, this is not a downgrading of its power rank. It is a refinement based on superior evidence. This figure still comfortably secures its position as the heaviest terrestrial animal for which we have reliable fossil remains. 77 tons, over 169,000 pounds, is the weight of a dozen large African elephants combined. It is a biological superstructure, a living siege engine that dwarfs any land animal alive today. This colossal size was not a matter of evolutionary excess. It was a life or death calculation written in the language of biology. Argentinosaurus inhabited an ecosystem that was also an arena, patrolled by some of the most formidable predators ever to walk the earth. The fossil beds that yield Argentinosaurus have also given us Maposaurus rosei, a giant carcharodontosaurid theropod that rivaled T-Rex in size. Crucially, fossil evidence suggests that Maposaurus may have hunted in coordinated packs. In this Cretaceous arms race, the only viable defense for a slow-moving herbivore was to become too big to kill. An adult Argentinosaurus was not just a meal, it was a mountain. Its sheer bulk was a fortress of flesh and bone, a passive deterrent so effective that only the young, the old, or the sick would have been vulnerable. Its immense weight was its ultimate weapon, the final word in a high-stakes dialogue between predator and prey. The evidence is clear. The true power of Argentinosaurus was its mass, a scientifically verified 77-ton statement of invincibility. From a few broken bones buried in the Patagonian dust, the tools of modern science have allowed us to reconstruct a living, breathing creature and place it on the scales of history. The debate over its exact weight will continue as new fossils are found and new models are developed, but the ghost of the 100-ton myth has been laid to rest by a clearer, data-driven reality. This journey reminds us that the fossil record is not a storybook, but a complex forensic file, one that reveals the brutal calculus of evolution and the almost unbelievable limits of life on Earth.